Hi there, I'm coming to you from the social distance of my backyard, so I just wanted to open the video by saying hi because this feels like such a weirdly impersonal way to do things and awkward for me also the first time through trying to do the type of presentation I would do on my iPad in a classroom setting. So I thank you for your patience. It will probably be Thursday evening before this goes up because as much as I thought I'll just go through it and not worry too much about ums and ors and coughs and background noises, it ended up being, I did need to make 3 or 4 videos and splice them together. So that will take, there you go, for reasons like that. That will take just a little bit of time and you should see this Thursday. I'm really sorry not to be there with you all in person. I mean, I know there are bigger things going on in the world than our particular trouble completing this course, but I just wanted to say hi and thank you for your patience and good luck, and I'll be in touch more soon. Trying to stay with roughly where the course went last year, which was essentially the first half of chapter 23. So 23 is on geometry and measurement, and when we measure a characteristic of an object, we're really matching that characteristic with something that we know something about, and we call that a unit of measurement. So whether I say that something is 12 feet long, I'm matching that with the known idea of the unit of something being a foot long, because we have a kind of a communal grasp of what that means. So that's called a standard unit, a unit that everyone understands what I mean, or at least most people understand what I mean when I say a standard unit. We can also use a non-standard unit. So in this example, if I wanted to find the volume of my bathtub, I could do it using a measuring cup that I know the size of. I know how much water it holds. Or I could do it using something non-standard, like my favorite coffee cup, my favorite coffee mug, and see how many coffee mugs of water are in the bathtub. Typically, of course, we use standard units. It allows us to communicate with each other. So advantages, disadvantages of standard units, well, mostly advantages really for standard units. We can communicate meaning to others more easily, especially if they're not actually present. So if I told you that my bathtub holds 53 of my favorite coffee cups, that doesn't tell you a lot because you don't know what size my favorite coffee cup is. But if I tell you that it's a certain number of gallons, that's probably more informative. So standard units allow us to communicate meaning when others are not present. Advantages, disadvantages of using non-standard units. I mean, the disadvantages are obviously it's hard to communicate to others. But advantages, for younger children especially, younger children, often in elementary school, it will give them a kind of a sense of involvement if they get to choose the unit that's being used to measure something else. And it can also give them a better understanding when they don't have the context, so may not have the context. For example, my daughter's 9 and she sort of now is getting to know what a foot is or what 6 inches is or 3 feet, but that's pretty recent. And I think children who are 5, 6, 7, even 8 years old may actually have a better sense if you tell them, it's about half your height. That means more to them than if you tell them it's 2 feet long or something like that. So our text often uses imperial units. I'm not going to hold you responsible for converting between imperial and metric units. but I will hold you responsible for knowing the conversions between metric units. So if you refer to our textbook, this is the image from the textbook. It has the metric prefixes all the way from the standard, the base unit, which is meters, going in both directions, so getting larger and getting smaller. And you should be able to draw some links between this and the work we did on scientific notation, because you can see that, for example, kilo, we talk about kilometers all the time, is really 10 to the third meters. So 5 kilometers is 5 times 10 to the third meters. Or if we look at, say, nanometers here, it's 10 to the minus 9. So if I said that something was 3 nanometers, that's 3 times 10 to the negative 9 meters. So this gives you a link between the metric system and the scientific notation that we did in Chapter 5. I'll talk a little bit more later about converting between units, both in the metric system and just a tiny bit outside of it. So let's talk about measurement. I remember having a conversation about this in Math 161 when we discussed discrete versus continuous quantities. And we talked about measurements never being exact no matter how precise they get. So we're going to draw a difference here between exact and precise. With the exception of times when we're measuring by counting, we need to keep in mind that our measurements are never exact. They are only a reflection of the tools that we're using to measure. So this can be confusing for children because we often are expected, or we expect them to assume that the measurements that we give them are exact. And so that can be confusing for them. But really, if I tell you that a rectangle has length 5 centimeters and width 2 centimeters. Sure, in elementary school, we might assume that kids are going to simplify and think that these are exact measurements, and the area is going to be 5 times 2, which is 10 square centimeters. But in real life, chances are it's not 2 on the nose. It's close enough to 2 that with the ruler I have, I can't be more precise than that. But it might not be exactly 2. So, for example, here's a ruler. And let's say I have marked off 1, 2, 3, 4, 5, 6. That measurement that I listed as 5 centimeters, well, it means that I'm reading it from here on the ruler. But with the level of precision of this ruler, it could really be anywhere kind of in this range, and you would probably give it as 5 centimeters. We can get into talking a little bit more later about when you would and when you wouldn't, when you might try to make an approximation of what that actually is. But for now, let's say, probably it could be anywhere from 4.5 to 5.5. And on a ruler that only has centimeters marked, you might reasonably describe that as 5 centimeters. And the same thing with saying that it has a width of 2 centimeters. That could be really anywhere between 1.5 and 2.5 centimeters on this particular ruler. Where we left off. Suppose I want to measure my height in terms of centimeters. If I have a ruler that only indicates centimeters, I personally would probably say that my height is 166 centimeters. But if my ruler also shows millimeters, I might be able to read it more precisely, and I might say my height is, I don't actually know this to this detail of precision, but say it's 166.3 centimeters. If my ruler only had every 10th centimeter indicated, then I might say my height is 170 centimeters. Or, I don't know, let's think about this a little. I won't draw all the way from the beginning, but suppose I have, 150, 160, 170, and my height falls sort of right here-ish. I actually think that we're inclined to average things, but only to average things, probably not to go more precise than that. So I have a feeling, at least personally, I would describe that as 165. So I wouldn't necessarily only go with the 160 or 170, but I probably wouldn't attempt to go more precise than just finding the midpoint between two of those measurements. So which is the correct answer to the question, what is my height? Well, it depends. None of those is exact. None of them is precise, but they're all reasonable estimates depending on how precise I need to be. Suppose I measure the length and width of a rectangle, but my ruler is only marked off to the nearest centimeter, and I find the length is somewhere between the 10 and the 11 centimeter mark, and the width is somewhere between the 4 and the 5 centimeter mark. So I have a rectangle, and my short side is somewhere between 4 and 5 centimeters, and my long side is somewhere between 10 and 11 centimeters. Well, a reasonable explanation for the size of this rectangle could be anywhere from the very smallest possible measurements, in other words, 4 by 10 or 40 square centimeters, up to the largest possible measurements, which would be 5 by 11 or 55 square centimeters. So a fairly big range here. Quite a large range between 40 and 55 square centimeters, but really anything in that range is a reasonable estimate for the area of the rectangle. The smaller the unit of measurement is, the better of an approximation I get. So if I measure the distance from the legislature to UVic only to the nearest kilometer, I'd find the distance to be 8 kilometers. But if I measure it in, going back to the metric table, if I measure it in hectometers, which are only a tenth as large as kilometers, because they're 10 to the 2 meters instead of 10 to the 3, then I might find it to be 78 hectometers, which is 7.8 kilometers. Now, if I measured it in centimeters or millimeters or even nanometers, I would have an even more precise measurement. But even if I measured it in nanometers, it might not be exact. In fact, it wouldn't be exact. I wouldn't have the exact value. I would still only have an approximation that was within a nanometer of the right distance.